Let's look at an example of how these apply in the real world. A reversible heat pump is a climate-controlled system that is an air conditioner and a heater in a single device. Operated in one direction, it pumps heat into the house to provide heating. Operating in reverse, it pumps heat out of the house by providing cooling. If some physical machines can run in two directions, we might ask if some of the function machines we have been studying can also run backwards. Figure 7.1 provides a visual representation of this question. In this section, we will consider the reverse nature of functions. Suppose a fashion designer traveling to Milan for a fashion show wants to know what the temperature will be. He's not familiar with the Celsius scale. To get an idea of how temperature measurements are related, he sends his assistant Betty to this week's weather forecast from Figure 7.2 for Milan and asks her to convert all of the temperatures to degrees Fahrenheit. Betty finds this formula online that relates Celsius to Fahrenheit. C equals G of F equals 5/9 times the quantity F minus 32. Help Betty convert the temperatures for her boss. In this case, when I substitute in 26 degrees Celsius for C, I can solve for the corresponding Fahrenheit temperature. In order to get the Fahrenheit by itself, the first thing I need to do is we'll multiply both sides by 9/5, which is the same thing as dividing by 5/9. And I get 46.8 equals F minus 32. So now to get the Fahrenheit by itself, add 32 to both sides, and we get 78.8 equals F. So this means that 26 degrees Celsius is equivalent to 78.8 degrees Fahrenheit. Now this would be a lot simpler if we actually had a formula where we inputted in Celsius and it outputted the Fahrenheit temperature, since we have the Celsius and I'm trying to solve for Fahrenheit. So what we can actually do to make the rest of finding these temperatures a little bit quicker is let's take this formula, C equals 5/9 times F minus 32, and let's solve it for F. So that way all we're having to do is input in the Celsius, plug that into our calculator, and we get the corresponding Fahrenheit. When I do that, I get C equals 5/9 F minus 160 over 9, which is what 5/9 times 32 is. So now to get C by itself, we'll add 160 over 9 to both sides. To get rid of 5/9, we would divide by 5/9, which is the same thing as multiplying by 9/5, which gives us an end formula of F equals 9/5 C plus, when I multiply 9/5 times 160 over 9, the 9's will cancel out, and 160 divided by 5 is 32. So now what I've done is I've taken this formula and I've essentially reversed it by solving for F. So now we're inputting C and we'll get an output of F instead of plugging in that output of C. Okay, so let's see if this is a little bit easier or quicker for us to do. So if I wanted to convert this 19 degrees Celsius and figure out what the corresponding Fahrenheit is, this should be a much simpler process. It's just going to be 9/5 times 19 plus 32, which when I substitute all of that into my calculator, I get 66.2 degrees. That was a lot quicker than having to go through all of these steps here. Let's actually see what this means and mathematically. The definition of an inverse function. Two functions are said to be inverses of each other if they are the reverse process of each other. In the example above, instead of inputting Fahrenheit and outputting Celsius, the new function inputs Celsius and outputs Fahrenheit. So it reversed the process. It reversed our inputs and outputs. We can notate this by using inverse function notation. So this function was called g inverse on the last slide, or not g inverse. This function was called g on the last slide. So we would notate that inverse function as g to the negative 1, which is g inverse. Using this notation, we could rewrite the function found in the last example as g inverse, and now our input values are c, is 9/5 c plus 32. So what we're essentially doing is saying, hey, this relates to the function g, but now it's going to be the reverse process where you're inputting in c instead of inputting in f, which is what we had before, which was this function. So this is just reversing the process. Note that a function f must be 1 to 1 in order to have an inverse. So this means that for every y value in the range of f, there is exactly one x value in the domain of f. So for something to be 1 to 1, you have these values. You just need to make sure that for every x that only goes to 1y, and that's how you know that you have a function. But the other way, so now we're not just looking at our x values and making sure that they go to only one value, but now we also have to look at our y values and make sure that those get mapped to only one value. So that's what it means to be 1 to 1. For every x, there's one y, and for every y, there's one x. Note that the inverse function f is denoted by f inverse, and this does not mean 1 over f. Okay, you're used to seeing something like x to the negative 1 power is 1 over x. So that works, and that property of exponents works when this is a variable that stands for a number. In this case, this is a letter, but this is what we're naming a function. So it doesn't stand for a number. This stands for the name of a function. So that's why the property of exponents, of having something to a negative exponent, does not hold true here. So whenever you see f inverse, this means to find the inverse function, not 1 over f.